Good morning, good afternoon, good evening, everyone, and welcome to AI for Good. I'm really excited for today's session. My name is Matthias Graschel. I'm a research fellow at Harvard Medical School and a member of the ITU WHO Focus Group on AI for Health. ITU is the United Nations Specialized Agency for Information and Communication Technologies and the organizer of AI for Good, which is an initiative of ITU together with 38 sister United Nations agencies, XPRIZE, ACM, and co-convened with Switzerland to see how AI can help to achieve the Sustainable Development Goals. If you're interested in learning what this focus group on AI for Health is doing, please reach out. We're always looking for people to join the effort. I have the immense privilege of introducing today's session as part of the AI for Health series, Making Neural Nets Uncool Again by Jeremy Howard. Jeremy is a data scientist, researcher, developer, educator, entrepreneur, and so much more. He's a co-founder of Fast.AI, a research institute which is dedicated to making deep learning more accessible. He's also a distinguished research scientist at the University of California at San Francisco. Jeremy has founded and led several other companies and initiatives before that. As a physician and a bacterial genomicist without any formal training in computer science, my research really relies on people like Jeremy, who write software like Fast.AI to make deep learning and algorithms more accessible, and thereby really enable people to engage with AI, no matter how likely their background. I can personally vouch for Jeremy being an amazing speaker and a great person when we met a couple of months ago to discuss this new book in our book club, and I'm sure he's gonna touch on this book today as well. So with no further ado, to the audience, please ask away during Jeremy's talk using the Q&A functionality. The listeners on Twitter and YouTube, you may wanna join the Zoom link so you can also engage in the discussion. Please, Jeremy, take it away.
Hi there, thanks very much. Now, I think your plan was to have a couple of bit of Q&A to start with. Is that still the plan, or do you want me to jump into my slides?
Yeah, jump into your slides, and then I think after 35, 40 minutes, let's jump into the Q&A.
Oh, okay, no problem. Better share my screen then. So this title of this talk is also the kind of the motto of our organization, making neural nets uncool again. And I'll try and explain what that means and why we actually think it's surprisingly important. So neural nets have been around for a while. This is the first one. This is the Mark I perceptron that was built at the Cornell Aeronautical Laboratory. And back in those days, neural nets were created with hardware and really not with software. So you can see there's a lot of actual connections going on there. So that was back in 1957. So neural nets are not a particularly recent phenomenon by any means. They've been around almost since the dawn of the computer age. The promise of the neural network is huge. Mathematically speaking, a neural network is a mathematical function which is provably infinitely flexible. So what we mean by that is there's something called the universal approximation theorem, which was developed quite a bit later than 1957, but we now know nowadays. And the universal approximation theorem proves that a neural network can approximate any given mathematical function to an arbitrary level of specificity, as long as you make it big enough. That assumes that you know what all the weights of that network are meant to be. So in theory, there's some neural network that can solve any mathematical problem you can think of, as long as it's computable. So then, the key question there is, well, how do you set the weights? How do you set the parameters so it solves some particular problem? And through most of the history of neural nets, people have focused on some kind of gradient descent, which probably most of you would have touched upon at high school or university, such as kind of Newton's method, basically approaches where you find out the gradient of this mathematical function, the neural network, and you follow it downhill to try and find the point where it best answers the question you're trying to answer. So gradient descent is an all-purpose parameter fitting method, which actually works extremely well to find the parameters of a neural network to solve any given problem. The problem was that the other two pieces, which is it needs to be fast and it needs to scale up to really complex problems, were not solved at this point by any means. And so I started doing stuff with neural nets, I guess in, just trying to think, maybe 25 years ago or so. And we did use them successfully to solve, genuine important commercial problems, but we were working on hardware that cost well over $1 million, and it was at one of Australia's biggest retail banks that I was working at, so only the biggest companies had enough data. So it cost a lot of money, and even then, it's the kinds of problems we could solve were somewhat limited, honestly. So the excitement about neural networks went away, and instead people used other approaches to machine learning, and in particular the approach described in this slide was and is extremely popular. This is from this paper in Nature. It's The Computational Pathologist by Andy Beck and friends, and it's it'd be like 2011, I guess, just before the latest neural net craze hit. And so what this paper was doing is it's saying, can we find a 5-year survival predictive model for, I think it's breast cancer? And so the way they did that was they said, okay, well, let's get the histopathology slides, and then let's create an epithelial stromal classifier. And then for those, lots and lots of experts, doctors, pathologists, computer scientists, mathematicians, many of the best in the world got together and tried to think about in these slides, what are the kinds of features that may indicate high versus low survival? And they came up with ideas like, relationships of contiguous epithelial regions with underlying nuclear objects and so on and so forth. So this is what's called in machine learning, the creation of your features. So there's lots of feature creation. And as I said, it required computer scientists and mathematicians, not just pathologists, because each one of these things had to be mathematically encoded and then turned into computer code. So there's many years of work for many, many people. But once you do this, you can basically grab all these features and throw them into a classic regression model. So this is classification, so a logistic regression model. And it worked extremely well, hence the Nature paper. So, the downsides of this approach is the amount of time, the amount of effort, the amount of expertise required. And even given all that, it's pretty hard to get superhuman performance. You can get pretty good performance, but it's hard to get superhuman performance. But it's still, it's a pretty good approach, and it's still used in many areas. Then in the very early 2000s and very late 90s, Bryman from Berkeley came up with the random forest, which is a bit like this logistic regression approach. You still need to create lots of features and so forth, but a lot of the work was done for you. And this is basically built on the back of these decision trees. So decision trees are basically a bunch of binary classification decisions. Then in a random forest, you create hundreds of decision trees on different random samples of your data. And this approach, and also a very related approach called gradient boosting machines, started to really take over. They needed a lot less expertise on the kind of the statistical side. They're a lot harder to get wrong. But they didn't really push us into new territory in terms of what's possible. It's more like they made what's possible kind of easier and faster. One of the really cool things about random forests is that they didn't just give you good predictions, but they also told you what things in the data were the most important in making those predictions, and they told you about the shape of those relationships, and they gave you a lot of insight into the data as well. So that's another reason that random forests got super, super popular. And so these are the tools that I used for, I mentioned I used a little bit of neural nets early in my career, but most of my career was kind of logistic regression, GLMs, random forests, and so forth. I became the #1 ranked competitor on Kaggle using these kind of techniques, and I gave a talk in 2011 about this kind of toolbox, which served me very well for a very long time. But I noticed something interesting happening in 2011, which is that suddenly neural networks reappeared. Not many people noticed, but they actually started winning competitions. And not just winning competitions on difficult things like recognizing traffic signs, so image recognition, but actually beating human performance. And so I kind of, because of the universal approximation theorem, I was kind of on the lookout, for the days when neural nets would reappear. I thought it would happen. I didn't know when, but I felt like this was the right way to do things. And so as soon as I saw this, I thought, wow, this is a really big deal. And I started to be kind of wonder about, well, how did they solve these problems? And so it turns out that what these guys had done is that they had figured out how to make GPUs, the graphics accelerators in everybody's computer. They figured out how to get them to do gradient descent on neural networks for us. And GPUs are massively, massively parallel, particularly for their price. And this made a huge difference. And one of the things that made a really big difference here was that the software that they were using was released as open source. So anybody could start to use GPUs to do gradient descent on neural networks. And so then we started to see on Kaggle, so here's Pierre, who's this guy here in this paper, winning competitions on Kaggle, but not just that, the kind of the jump in the state of the art was something like we'd never seen before. So this competition, which is to can you recognize dogs versus cats, when the competition started, 80% accuracy was the best that anybody had done. And that was with a whole lot of kind of domain specific stuff, lots of expertise. And this competition, which lasted just 3 months and people working on it part-time, they got to nearly 99%. So the error rate dropped by 20 times. And so that was, I was thinking like, okay, this is something I've never seen before. I've never seen a technology that just jumps so far. And it's not just at this point that they were fast, but they also figured out how to make it scalable. And the solution to that was not just to create neural networks, but to create deep neural networks. And so deep neural networks basically means neural networks with lots of layers. It turns out that this infinitely flexible function, if you only have one hidden layer, you need exponentially more activation, more compute. But basically, it's not feasible in practice. But if you make them deep, then they actually scale really well. And over the last few years, there's been a couple of particularly important developments that have allowed us to train really deep networks, which are batch norm, stands for batch normalization, and skip connections. Now, the details of those don't really matter, but I'll show you a picture of what it looks like. This is the surface that the gradient descent algorithm has to navigate in a normal deep neural network. But if you add these things called skip connections, this is the surface it has to navigate. And so remember I said, gradient descent is basically figuring out which way is down and then following that direction. You can imagine here, if you follow it down, you end up in this hole over here, or this hole over here, or this valley over here. It's very hard to actually find the best bits of this lost surface. So with these developments, basically, researchers had figured out how to actually use really deep nets in practice. And nowadays we have networks with, up to 1,000 layers. We don't need that many. You don't often use more than 100, but it's there. It's a lot more than one, that's for sure. So this has just been extraordinary in terms of what it can do. And if you look at the kind of latest capabilities of these deep neural nets, here's an example from, I think this year, DALL-E, which was from OpenAI. These neural networks now, you can train them with pairs of images and captions. And then you can literally write any English you like. So here's an English thing that a person wrote, an illustration of a baby daikon radish in a tutu walking a dog. And the neural network will draw what you asked for. And here's various versions of what it asked for. And it's important to recognize here that this neural net has never before seen an illustration of a baby daikon radish, let alone in a tutu, let alone walking a dog. It's totally independently come up with this. So in this case, the human wrote an armchair in the shape of an avocado, which I can't imagine is something that's ever actually been seen before. And the neural net drew these pictures. These have not been retouched. They're not being cherry picked. This is just what it's come up with. So you can see that the capabilities of modern neural networks are quite extraordinary. And so that has made deep learning and neural nets today very, very cool. Everybody wants to do it. There are, lots and lots of money involved, lots of PhDs working on it. And another good example of this is the AlphaGo Zero, which you may have heard about from Google. They used deep learning to basically solve the game of Go. They absolutely thrashed the world's best players. And this is interesting because, when I was growing up, I was always told this is something which in my lifetime, we would definitely not see a computer ever win against a strong Go player. And here was something that in 3 days, without any manual feature engineering or without looking at anybody else's games, taught itself to play at a level far beyond any human. One of the really interesting things about these deep learning examples is how actually simple they are. This is the code for the important part of AlphaGo Zero. This is the code that figures out how good a position on the board is. And a couple of interesting things about it. The first is it fits on a slide. And the second is if you've ever looked at any neural nets before, such as the kind of neural net you might use to recognize dogs from cats, you would recognize this as being almost exactly the same. So, one of the really interesting things about deep learning is once you learn the basic techniques, nearly every problem you solve looks really, really similar. And this is a really important point because it means that people can use deep learning for solving lots of different kinds of problems without having to learn totally new techniques again and again and again. So because deep learning is so cool, and because it's cool because it actually works so well, deep learning is now used very widely, and it's a state-of-the-art approach for all of the things that I've listed here, and many, many more. So, for example, Google uses it quite widely in its web search tool. It's used by Amazon for their product recommendations. It's used for things that involve a lot of money, and it's increasingly being shown to be effective in medical imaging. Obviously, the rollout of it in practice is pretty hard. So it's more talking about the underlying capabilities rather than actually getting it out there in practice. Although, in places like China, there is quite a lot of deep learning appearing actually in clinical use now, and so forth. So in 2013, 2014, I felt like I couldn't just stand on the sidelines and watch this. I needed to get involved. I wanted to use this tool to do something important. And at this time, deep learning was not being used in medicine at all. And people weren't even writing any academic articles about it. But I was surprised about that because I felt like there should be opportunities to use deep learning to help meet the huge shortage of doctors worldwide, help make doctors more productive or take some of the burden from them. And so I put together a small team, 4 people, to try doing something interesting for the first time, which was to guess whether or not a nodule in a lung CT scan was malignant or not. And we spent 2 months on that, and then we compared it to a panel of 4 human radiologists doing the same thing, and ended up with a better false negative rate and a better false positive rate. And I was very excited about this. I was pretty surprised in some ways. It always feels kind of magical when you actually get one of these models to work. And I really wanted to tell the world about this because I felt like this is something that everybody should be getting involved with. This is such a powerful tool, and it seemed like it could help so many people. So I tried to get the word out, and we had some success with that. And CNN talked about us, lots of people talked about us, and very rapidly, the idea of using deep learning in medicine kind of took off. So that was great. And I really enjoyed that time. But what I did notice is the vast majority of people doing deep learning at that time, it was a very homogeneous group. They were basically all, extremely privileged white men who worked at basically one of 5 particular academic institutions. I mean, all good chaps, a lot of them were friends, but they weren't a diverse group of people solving a diverse group of problems. They, all tended to be focusing on kind of web search algorithms or photo collection, sorting things, or stuff like that. And I was looking like, where are the people working on earthquake resilience or access to water or improving education or whatever? And it wasn't happening. And part of the problem was that you can only solve the problems you know about. So for example, if you're not a doctor, you don't know what kinds of problems doctors need to solve, and so you don't solve those problems. And so I speculated that the right way to solve this problem was not to try to teach this very small group of homogenous people about what are all the world's problems and why should you try to solve them and where's the data for them and what obstacles are people facing. But instead, we should try to put deep learning in the hands of domain experts. In this case, for example, in the hands of doctors or in the hands of journalists or in the hands of lawyers or whatever. So this was, as I said, it's pretty speculative because nothing like that had ever been done. And it was all about taking deep learning out of the kind of the world of the cool, flashy stuff, of huge banks of computers working on huge amounts of data to solve really flashy problems, but put it in the hands of normal folks solving normal day-to-day problems. Using normal types of computers and normal amounts of data, not this kind of flashy stuff at all. And so my partner, Rachel, and I came up with this idea of creating a new organization called Fast.AI that would be dedicated to making deep learning accessible. And so by accessible, we meant getting rid of the constraints. making it so it's not an exclusive endeavor anymore, but it's extremely inclusive. And so to do that, we thought, well, okay, we should probably start with education to like show as many people as we can how to use the tools, techniques, technologies that are already available. And then we should recognize where those fall short and write software to make things easier. And then as we write that software, we'll find the things that where there are constraints in terms of amounts of compute or amounts of data or amounts of expertise required or whatever, constraints that we can't solve with software, and we'll do research to try to figure out how to get past those constraints. And then we hoped that out of this, we would have lots of new deep learning practitioners using our software and coming out of our education. And so we would build a community to allow them to help each other so that this would not be a kind of lonely experience. So I'll start by talking about how we tried to use education to try to make deep learning more accessible. So we created a course, and you can see the course at course.fast.ai, and it's possibly the most popular deep learning course in the world. It was I think really the first complete course, and we refresh it every year from scratch. And it's very focused on kind of the practicalities of getting people to actually use deep learning to solve real problems in practice. And it's been really fun to see what that looks like. After the first week of the class, we get people to go onto our online forums and tell us about what they've built. And we've had, over 1,000 replies. Some people do fun little things like this cricket versus baseball classifier that one of the students built, Nicole Balaji. But one of the interesting things about this is this was perfectly accurate on a held-out validation set at recognizing cricket from baseball, and it just used 30 training images. And so we spent a lot of time doing research and building software to help make it kind of bring down the barrier of how much data you need. And as you can see in this case, Nikhil built a fantastically good classifier with just 30 images. Other students built models to recognize different types of people from their homelands, zucchinis versus cucumbers. Oh, this was an interesting one. This person wrote something that could figure out what part of the world a satellite image was from. With over 110 classes. It's a pretty difficult problem to solve. Different types of bus, different types of batik cloth classifier. That's just another interesting one, not just a classifier, but actually segmenting images to kind of figure out, the conditions of buildings and this kind of stuff is very important for disaster resilience and stuff like that. So as you can see, it's like after just a week or two, students were doing really interesting work. And even some of the work was actually reaching the state of the art. So one of the students tried doing the Devanagari character recognizer and broke the previous state of the art results. Somebody else did something for environmental sound classification and got state of the art results. And one of the students actually in the first class built this interesting thing at Splunk, which is a big NASDAQ listed company, where he actually created a new patented algorithm that they built into their products for finding fraud with behavior biometrics. Another student went on to create a new startup to help visually impaired people see. Another student worked on genomics with some fantastic results, and so forth. So over the years since we started that, we've had well over 3 million views of those videos. So they've been super popular, and that's been great to see. And also we've got a lot of good feedback. For example, on YouTube, as you can see, over 2,000 people liking it. Apparently 21 people still don't know how to convince those people. Maybe they just picked the wrong button. And as Matthias mentioned, we've also got a book. So the book is basically has the same stuff that's in the course. And so, one of the interesting things about Fast.AI is we're not a commercial enterprise. All this stuff that we put out there is available for free, including the whole book is also available for online for free as well. And folks like Peter Norvig, who runs research at Google, saying this is one of the best sources to become proficient at deep learning. So lots of people, really liking this education stuff. And so we now have tens of thousands of people out there in the world who have become very effective deep learning practitioners and have brought that expertise into their own organizations all around the world. And we also now, have a big community of people who are helping each other out. So the problem was that, education's not enough. We found lots of places where the amount of data you would need or the amount of compute you would need or the complexity of things, it's just too difficult or too expensive. So we've done a lot of academic research and had some great results. One great result was research we did into improving the performance of training neural nets. So in 2018, we entered a competition called Dawnbench, competed against folks like Google and Intel, all the big ones, and we showed that we were able to train ImageNet, which is at that time, if not still today, the kind of most important computer vision benchmark. We could train it cheaper than anybody, fastest on publicly available hardware than anybody, fastest on a single machine than anybody. Our single machine entry beat Intel's entry that used 128 machines. And later that year, we weren't just better on GPUs, but our GPU result even beat Google's TPU result. And so this was really important research for us. And you can see this is us with some of our students working on the competition. Because again, we were trying to make neural nets uncool, which is to say, all right, you might think it's cool to use 128 machines in a huge server cluster, but what if we can, do better than that with a machine you can hire for 40 cents an hour from AWS? So we're trying to. What we really mean by uncool is we're trying to make it less exclusive, and we wanted to show the world that. That anybody could do it. You don't need, a PhD. You don't need millions of dollars. You don't need millions of rows of data. And so, this result got, again, a lot of attention, which was really important for us because there's no point, finding some important insight if people don't know about it. Hopefully this helped to break this common view that only the Googles and Intels of the world can actually, make a difference in deep learning. So that was a great result. And a lot of people commercially also noticed this, and really this research was all about kind of using common sense and some simple techniques to make things much faster. And so NVIDIA, talked about our results in their marketing, and even Google, who we had beaten, then went on to incorporate our optimizations to make their Dawnbench entries even better still. So the research is not really useful if it just ends up in an academic paper. It needs to be something that people can actually use. And so for that purpose, then we write software that makes all of those research results readily available to anybody. And so our software is called Fast.AI, and we released our first version in 2018. It's a library that sits on top of PyTorch, which is a very popular deep learning library, and nowadays it's the most popular kind of API for working with PyTorch. And it's been really successful. People really like it, and for a number of reasons. One is that compared to the kind of other popular API, which is Keras for TensorFlow. Fast.AI can be quite a bit more accurate. It can run quite a bit faster. And actually, most importantly, it requires a lot less code. It's not that typing code takes a long time. The issue is these 31 lines of code you need with Keras are all things that you have to learn what to write. And if you get any one of those things wrong, you're going to have problems. And so we try to make it so that you kind of think of a problem you want to solve, you think of a way you want to solve it, and then you can get it down as quickly as possible, and the computer doesn't make you write things that it can figure out for itself. And that's what really these kind of small number of lines of code is all about. And so something else we did with the library to make it as accessible as possible was we tried to write really great documentation. So here's an example of one of the functions in the library. And so the documentation kind of has links to the papers describing the things that are being implemented, and it has pictures of what it's doing. And then everything actually in the documentation is all available on a Google platform called Colab, which is an interactive computing platform where you can click a button on any page of the documentation, and it actually pops up the code that created that documentation, so you can start experimenting with it. So again, the idea is to make it, this as unexclusive as possible, so that like you can literally see how we implemented everything in our docs, and you can play with it, you can use it, you can copy and paste it. So really making it as accessible as possible. So a lot of people have switched to Fast.AI in the last few years, and when they've done so, people are finding, for example, compared to their TensorFlow models, they're telling us that they're getting much, much better results than they did before. Here's another example from a founder of this company. We had tried TensorFlow before. We spent months tweaking. We used Fast.AI, and it just took a couple of days to get better results. And so this is really about all that research I described being implemented in the software so that end users get good results, straight away. Oh, this is a ITU person. There you go. We actually went on to create a new version of the software last year, Fast.AI version 2, which is a big advance again. And we've actually written an academic paper about exactly, the underlying foundations and theories behind how that all works. But one of the really important parts, again, for increasing accessibility is that regardless of how you want to use Fast.AI, you're going to write almost exactly the same code. And it's generally going to be 4 or 5 lines of code. So here are the lines of code necessary to create something that recognizes cats from dogs. As you can see, it's very short. Here's something which can color code every pixel of an image according to what object it is. And as you can see, it's almost the same code. And so here's an example of it color coding the cars, the road, the lines, and so forth, trees. Here's the lines of code necessary to guess whether or not a movie review is positive or negative sentiment. As you can see, still very few lines of code, and it's nearly the same lines of code. Here's something to do collaborative filtering. So this is to create a recommendation system to figure out which users might like which movies. Again, very few lines of code, pretty much the same lines of code. So this is important for accessibility because people who are not full-time neural network researchers, they've got a job to do. They're a doctor, or a radiologist, or a lawyer, or whatever. They can't be learning 1,000 different APIs and lots of little different details and boilerplate stuff. And so with this, it's just a lot less learning required to get going, to get good results. And even for researchers, it frees up a lot of kind of brain space to focus on what you care about. So this software we wrote, the thing I was just showing you is what we call the applications layer. It's a thing where you can kind of write a very small amount of code to solve a problem. But most of the time, you want to solve a slightly different problem, possibly to the kind of the standard ones. There might be some little tweaks you want to make. And so one of the interesting things about the Fast.AI library is it has this layered API where you can dig deeper and deeper and deeper and change absolutely everything. So for example, looking at the mid-tier API, oh, actually I didn't have those slides there, so ignore that box. Okay. Oh yeah, actually that's probably a good time to stop anyway. Yeah, so between the software library that kind of makes it, well, each year that library's been getting better, and it's been nice to see that each year that means we can teach more stuff here to people with less prerequisites in less time. And so we kind of have this iterative cycle now between our education and our research and our software, where each year all of those things kind of help each other, and we aim to get end up with practitioners each year who are more effective, have to spend less time studying, and can build cooler stuff. Yeah, that's about that.
Thank you so much, Jeremy. Please imagine a big round of applause. That is, of course, in the virtual format, not possible. Thank you so much for walking us through your journey from generalized linear models to random forests to neural nets, and how you've really democratized the field for so many researchers. I want to start the discussion with a question about why is it that deep learning, AI, ML is so prevalent and really industry standard in the financial industry, in the entertainment industry, but medicine and healthcare is having such a hard time to really make use of these algorithms on a day-to-day basis?
Well, as the founder of the first company in that space, I can definitely talk about that. The technical challenges were much less substantial than most people think. There's a lot of kind of talk about difficulties in taking an algorithm and using it in a different hospital or with different equipment or what it was trained on or whatever. But those are actually very easily solved with a little bit of fine tuning. The challenges we had were more regulatory, political, financial, and cultural. So on regulatory, there isn't really a way to, at the moment, at least in the US, to get an algorithm approved which can continue to learn. So if I train my algorithm now, then in 2 months' time, I've got 2 months more data to improve it on, and different medications or a new CT scanner or whatever. If I just use exactly the same thing with this extra data, I now have to get it re-approved. And even doing it once is so hard that basically almost nobody wants to even try it, and it's keeping people out of the space. As I say, in China, it is being used quite widely now, particularly in medical imaging. I think maybe they have a regulatory environment which is a bit more conducive to that. I mentioned financial. That's a US specific issue, which is that a lot of the hospitals I spoke to said that they were concerned that what I was describing, which is basically two things. I was focused on medical imaging. Radiologists can do things in less time, and they can get it right, so there'll be less hospitalizations. And so the concern from hospitals was, that sounds great, but that's going to have a really bad impact on our bottom line. If our radiologists are more efficient, then that means we're charging out less hours. And if there's less hospitalizations, that means we have less customers. So even though in theory, hospitals are meant to get people sick quickly and efficiently, in practice, the American system isn't really designed for that. The cultural thing, there are lots of cultural issues, but one of the ones I really struggled with was medicine is highly specialized. And so anybody who's a really senior expert in medicine is a really senior expert in a specific thing, like a subspecialty. And neural nets are extremely general purpose. So it's actually technically not that hard to create a fairly general purpose kind of diagnostic system or kind of next best action recommender or whatever. But I just couldn't find medical experts who were interested in that. They wanted to focus on meningioma or prostate cancer MRI or Alzheimer's or some particular feature of Alzheimer's. So there wasn't a great fit there because you kind of end up basically solving 100 different problems in exactly the same way, but every one of them, the data is coming from somewhere else. It's in a different format, and you've got new people you have to explain how it works to, and nobody talks to each other. So yeah, there's lots of kinds of issues around medicine, particularly in the US, that makes it difficult, even though I'm convinced it's actually the biggest opportunity area. That's why I focused on it. And I do think that places like India and China are actually the places that's going to make the biggest societal impact. They're the ones that actually have the shortages of doctors. So they're the ones who need to solve this. And we're seeing it happen. And I think places like the US and the UK will then be a follower in that space.
Okay, thanks for your thoughts. I'd like to give the floor to the audience. Please submit your questions. And I'll start with a question from Magnus Hellet. And he's asking, would it be possible to use deep learning to predict an individual's potential networking in, for example, lifelong learning? And he's giving the context of bridging education and jobs.
So as a rule of thumb, the answer to the question of can I use deep learning to do X is that you just have to step back and say, well, could a human do X on the basis of looking at some data? So I'm not very familiar with that particular domain space. But if it's something that you could say to a smart, thoughtful, patient, tenacious human, here's lots of data about this problem, can you use it to solve this other problem? Then a neural net should be able to do it as well. Or even if it's something you could give a huge group of people, neural net could do that as well. Based on the description of that particular problem, it sounds like the kind of thing that we probably wouldn't use a data-driven approach for, but more would be like, I don't know, interviewing people or talking to their families and teachers or something like that. So it might be less appropriate, but anyway, there's the rule of thumb you can kind of use for that kind of question.
Great. Mani has been asking, you mentioned conformity approvals of AI and how this can be managed for a continuous learning system. There's a lot of interest in certifying AI solutions. What do you think as key principles or aspects of such AI conformity schemes?
Yeah, I think one of the important things about thinking about AI solutions or AI products is to think about the holistic view. So don't just think about the algorithm, but what's the whole product that's being sold? So where are humans in the process? Where is AI in the process? How do they interface? What exactly happens end to end? Is there some kind of review? Are edge cases identified? How are they dealt with? And so I think, that whole system is the thing that should be studied. And then the outcomes of that whole system should be the thing that we care about. Whether or not the algorithm, in the middle of it is retrained with an extra 2 weeks of data, who cares? What matters is has a thoughtful, holistic, end-to-end system been identified? Does it handle unexpected situations? Does it handle changes to the data distribution? And these kinds of things are not often done. So for example, a lot of machine learning being used in the judicial system. It's also being used a lot in healthcare around kind of policy things around like, should people get health insurance or should they get, state support or whatever. And in these places, there's, very often limited, if any, human review. There's generally no appeals process. And, as a result, you kind of end up with all kinds of horrific stories of kind of Kafkaesque nightmares of humans against the machine, So that's how I would like to see people thinking about kind of judging AI-powered products.
Okay. Yeah. Nikos is asking if you know of any examples how deep learning is used in the production of food or food safety.
Sure, yeah. As it happens, I gave the keynote at the World Congress on Animal Husbandry a couple of years ago. So I did a lot of research into this. Yeah, I mean, look, honestly, deep learning is being used everywhere, and just I didn't know anything about animal husbandry myself before I gave this keynote, so I just did some googling around to see, and I was like, oh yeah, okay, it's used all over the place. And some of the applications I didn't even understand because it's not my field, but there was things around like a lot of the stuff in there is around kind of the audit trail, for example, of like recognizing an individual animal and seeing exactly how it goes through the process and is it handled correctly, and stuff like that. Um, because a lot of stuff in food handling is kind of visual, it's actually a really good area for neural nets to get involved because they're extremely good at recognizing things and recognizing when things aren't as they should be and stuff like that.
So Tristan is asking an interesting question. He's asking, how can you make sure that your students are not burning more resources and the training of neural nets bring advantages for good?
We can't be sure of anything, my approach is to, you know, do our best to make information available and to make the tools as good as we can. And not everybody's going to use it well. I mean, it's not just a case of burning resources, but some people are going to use it for applications I don't morally agree with. For example, a lot of stuff kind of being rolled out in predictive policing or face recognition of protesters or, stuff like that, which I hate. But, I've found that overall, by far the majority of our students and software users, when I talk to them, they're doing stuff which I'm just like, oh, that sounds really cool. And overall, I think it ends up with like, I don't know, something like Wikipedia. You kind of put something out there that people can put crap on, or they can make a genuine attempt to be helpful on. And overall, thankfully, in humanity, there's generally more people trying to do good than bad.
Madawan has a brief question. He was interested in what's the best source to obtain publicly available medical data sets to practice deep learning.
You know, the best way to practice medical deep learning is not to use publicly available data sets, but actually to get in touch with, an academic medical hospital or something like that near you and help them. Because there's a lot of people, almost everybody I talk to at academic hospitals, the professors all have ideas of stuff they want to use AI for, and very few of them know the people to do it, or they're, don't really know how to do a good job of it. And publicly available data sets are always, in medicine, by definition, going to look very different to real world data sets, because to make it publicly available, you do have to do a lot of stuff to it. Having said that, the well-known mimic data sets are pretty great. There's medical imaging ones, there's reporting ones, there's tabular ones. And, if you look at somewhere like Kaggle, there's quite a few kind of competitions, particularly around the medical imaging side. So yeah, you can certainly do some initial play work. And the Fast.AI library has a fast.ai.medical sub-library that has tutorials and shows you how to use certain publicly available data sets. But yeah, I would say as soon as you can, try to try to work with people who are actually at the coalface of this, and they'll have lots of data. Every hospital has lots of data.
So Jao Costa is asking, I think, a great question, also to wrap up the discussions. He's asking, so this is now probably since 2011, the third heyday of deep learning, of AI, of ML, and he's asking, can we already think about a next generation deep learning, and what will that entail? How will that look like?
Yeah, I get asked this question a lot, and I guess I kind of question the premise of it. Like, I feel like we're just scratching the surface of the tip of the iceberg around what we can do with this amazing technology right now. And, it feels a lot to me like, I remember when I was 18 and I was in Australia, and, I'd just got on the internet for the first time. There was no commercial internet providers in Australia. There maybe was a couple in America. It was very, very new. And I just started working at McKinsey at a management consulting company where we were doing all this kind of corporate strategy stuff. And I remember saying to everybody, this internet thing, it's going to be huge. It's going to change everything. And people would kind of ask me like, well, how exactly? What exactly will the world look like post-internet? And I had no idea. I couldn't have predicted exactly any of these things, but like, it was very clear it was going to touch every part of life, and that it would take decades for that to happen. And so I think, the coming decades are actually going to be about like, how do jobs and society and occupations and processes and everything adjust with this technology? And that's going to be a lot of work for a lot of people. And it's not clear to me that we need some kind of next generation of AI. We already have a universal function approximator. I'm sure there'll be continuing tweaks to make it a bit better and a bit better. But we won't necessarily have some kind of like totally different thing, because we already have a thing that we have no idea how to fully utilize it yet.
Okay. Well, Jeremy, we're at the hour. Let me thank you again on behalf of everyone listening, including those on Twitter and YouTube live streams. We're curious to see if the audience liked our AI and health session. So we're going to launch a quick poll that'll pop up at your screen. It has a smiley face for easy reference. And please just let us know if you would recommend the seminar series so we can justify inviting more speakers and having more sessions in the future. If you're interested in learning about AI for Good, about the ITU WHO focus group on AI for health, please reach out, find it on Google, and we're always happy to hear from people interested. I would like to once again thank everyone, our speaker, Jeremy, our participants, partner sponsors, and the co-convener, Switzerland. And I wish you a great weekend, and see you next time. Bye, everyone.
Selector, rewind selector, rewind selector, rewind selector, rewind selector.